Assalamu alaikum everybody. Hi and welcome to the second part on millimeter wave technology for 5G and beyond systems. So in this part, in the previous first part, we talked about the the definition of millimeter wave, the key characteristics and feature of it, the differences between millimeter wave and microwave, why do we name it millimeter wave, what's the difference between these two systems in terms of antenna design, number of antennas, channel characteristics and features, and so on and so forth. And we understood the key main challenges facing millimeter wave and some of the prospective solutions to address them and solve them. And we mentioned that MIMO and millimeter wave are kind of couples. They come always with each other. You cannot separate them from each other because millimeter wave alone does not function properly. And MIMO is kind of the technique that can solve many of the issues related to millimeter wave, mainly by using beamforming concepts at the transmitter side and also deploying many antennas at the receiver side so that you increase the receiver aperture and accordingly you increase the receive power, you enhance the signal to noise ratio, you reduce the interference, you reduce the amount of noise, and also you overcome the problem coming from propagation loss due to distance. So that's why MIMO is the key technology, the key enabling technology for addressing many of the problems that exist in millimeter wave band. So what are we going to do here is basically explain the main MIMO schemes that have been proposed and used for millimeter wave communication system. So basically we will talk and have a look at analog beamforming. In analog beamforming, the beamforming is implemented at the analog part of the transmitter and receiver. It's not implemented in digital form, in the digital baseband. And the reason for that is the cost of hardware, the complexity of implementing the hardware in baseband, and the power consumption due to the ADC components in the transmitter. To avoid these problems, we use analog beamforming. So basically you generate your signal at the transmitter and it goes through the baseband and you have one DC, digital to analog, and then you have the RF chain, which is composed of filters, amplifiers, and oscillators, and many other components as well beside that. And then you send your signal through different antennas, and these antennas, they have phase shifters. These phase shifters, we adjust the phase based on the angle of arrival with respect to the receiver in such a way that when you adjust the phases, you produce a narrow beam towards the receiver. What's the advantage of having a narrow beam? You reduce the interference to the other users who are located maybe here, maybe here, maybe here. The beam for this user doesn't go to the other users. This is one thing. The second thing, since you reduce the beam width, and I told you the amount of energy is confined, is the same, the beam can go to larger distances, can reach further distances. So you improve the coverage, you reduce the interference, and mitigate the effect of propagation loss due to distance. And if the receiver also uses another analog beamformer, the receiver will be able to capture only from the intended beam while not receiving from the other beams, reducing the interference, also reducing the noise, which means improving the signal to noise ratio, and accordingly you can receive your data with a very high reliability, as long as there are no objects between them, no obstacles. If there is any, the link will get cut and problems will start to occur, and you need some alternative solutions to handle this such scenario or situation. So analog beamforming is the easiest beamforming MIMO technology, and it's being proposed to be used with IEEE 802.11ad, which is WiGig, Wi-Fi access point, and it's being implemented in wireless high definition, wireless HD. And the main, why did we choose this? Driven by power consumption and hardware complexity. We cannot perform the beamforming in the baseband here, in the baseband. Usually, for the some of the students in this course are working on MIMO, transmit beamforming, or space-time block coding, or spatial multiplexing. Most of the techniques you are implementing and working on are in the baseband. You process them in the baseband, and there is no issue in that because the number of antennas you are having in your simulator or in your system is very low, like 2, 4, 8 maximum. But when you go to millimeter wave and you start talking about more than 20, 40, 60, even 256 sometimes, the complexity of dealing with this structure at the baseband is prohibited. Too much complexity that you cannot afford, and this complexity comes up with power consumption, and especially if you are going to implement in baseband, you need to have money digital to analog blocks, money RF chains, and this will insanely increase the cost of your transceiver design. And for companies, cost is the most important single factor to look at, because you can only compete in the market, you can only propose a new technology that can improve people's life only when there is a product that can serve the desire of the people and increase the internet and applications, while providing it with very low, cheap cost. This is the parameter that always differentiate companies from each other. Second point that we need to mention about this analog beamforming concept is the fact that it's basically suitable for only single stream transmission. Single stream transmission, it means you can serve only one user at a time, yes? Imagine you are deploying a base station and access point that can only serve one user. This is not very desirable, yes? With the current Wi-Fi access point, multiple users can access the access point and get data and get connected with it. But due to the complexity, the hardware complexity, the power consumption, these type of difficulties at 60 gigahertz, we cannot, with analog beamforming, the technique that was proposed for WiGig standard, and which is basically manufactured in a product called wireless HD, you cannot transmit more than one stream, and this limits the applicability to only one user or multiple users, but you are switching the beam very quickly so that you can serve them. And therefore, multiple stream and multiple user is not possible with this technique. And therefore, most of the research on millimeter wave MIMO is basically to enable millimeter wave MIMO to work for multiple users, to serve them all simultaneously at the same time. And this can be feasible only when you create multiple beams. And to create multiple beams, you need to somehow tolerate some complexity and power consumption. You need to break some of the constraints so that you can provide multiple streams. Of course, this technique, analog beamforming, requires joint search for optimal beamforming and combining vectors. At the transmitter, we call it beamforming. Yes, the vectors, beamforming. At the receiver, we call it combiner, not beamformer, combiner. And this basically, there are vectors or code blocks that you can adjust and use so that you can get your data reliably. So this is the single most important, the first single technique that was proposed for millimeter wave technology to address the problem of propagation loss, interference, improve the noise, and this and that. But as you can see, it has the problem that it can only serve one user. It cannot serve multiple users, and therefore it doesn't have too many advantages or merits that are attractive enough to the industry. So what else we can do? To solve this problem, the researchers have proposed recently new techniques that combine the processing of the analog domain with the processing in the baseband domain. So they say, instead of just using a digital to analog converter, one RF chain and one RF beamforming, you should be a little bit tolerant and accept the fact that you can increase the complexity of your system a little bit and allow us to use more than one RF chain. More than one RF chain means multiply the cost by the number of RF chains you are introducing to your receiver or your transmitter. If the cost of designing one transmitter receiver using analog beamforming technology is $100 or $1,000, and you are coming to hybrid beamforming, then the cost will be multiplied by the number of RF chains that you are employing and deploying in your transceiver. And suppose you are using 10 or 12 or 100, you need to multiply that 100 by that 1,000 to get almost $100,000 increase in cost. And for most companies, they say no customer will be able to afford such cost. And therefore, they try to be away from this. But they say, look, hey, where are you going? But this can provide the service for many users simultaneously. Like you are talking about 10 users, 100 users, you can provide them with this access simultaneously. So you say, instead of deploying 100 analog beamforming access points, I can deploy here only one hybrid beamforming access point that can serve 100 users, but while accepting the fact that I can increase the complexity of the system by increasing the RF chains. So it makes compromise on power consumption, hardware complexity, because you are doing some of the processing partially in the baseband processing, and some of it will be in the analog part where you have phase shifter also here. That's why we call it hybrid. Hybrid means that the processing is split among analog and digital. When you move to digital with millimeter wave communication, the complexity will insanely increase significantly. So power consumption and hardware complexity increases compared to the previous method, analog beamforming. Hybrid analog digital precoding enables spatial multiplexing and multi-user MIMO. This is the key motivation for this technique. This is why we are proposing this technique, proposing it in order to serve multiple users at the same time, which can be done by spatial multiplexing. Spatial multiplexing means one antenna, one access point can generate multiple beams, and these beams are not interfering with each other, multiple of them, and these beams can be allocated, each one of these beams can be allocated to one single user that can get connected to it and get the data from the transmitter. So assume this base station and you have a receiver here and multiple receivers actually, and each receiver is connected with one beam. So digital can correct for analog limitation, kind of supplementing the analog concept, but unfortunately it comes with some complexity. Approaches baseband digital performance can exploit sparsity and some other features in the channel. But nevertheless, this technique brings too much complexity and increases the cost significantly unless you convince the customers or the company that you are going to serve many users simultaneously, and this cost should be lower than analog beamforming in order to be accepted in the industry. Is this employed right now? It's not yet. Practically, it's not yet. It's in the research phase, in the research domain. But whether it's gonna be employed or not, or of course there is a need for that, and I believe most probably they are going to push for it, and it's gonna be, we are going to see it in the coming future products if we are able to reduce the cost a little bit more. So now this we have analog beamforming, we have hybrid beamforming, which combines analog and digital, and we have ultra, the third solution, ultra low resolution receivers. So in this case, since most of the complexity is coming from using RF chains and digital to analog, analog to digital, so in this case I can use, instead of using analog to digital converters, which are here placed, that are extremely complex and have many bits. Like the more bits the analog to digital converter has, the more levels you can use to quantize your signal, and therefore the quantization noise, the quantization error will be less, which means that you can reconstruct your signal with less errors, with less noise, quantization noise. And to do that, you need to have a high resolution analog to digital converter. But since I am in the millimeter wave band and there is constraints on the power and complexity, and I cannot afford that, I can instead use 1-bit analog to digital converter. 1-bit analog to digital converter means 2 levels or 1 level. And your signal, if your signal is something like this, you quantize it something like this. Yes? If it is sine up, it's rect up. If it's sine down, it's rect down up. And then you go to baseband processing. It uses 1-bit ADC pair for each RF chain. It provides ultra low power solution. Of course, I am kind of reducing the resolution, and the signal will not be exactly the same. But what's the point here? I'm reducing the power consumption at the receiver, so that your receiver, your mobile phone, does not get heat, does not becomes like heated and generates heat, and you feel that it's unaffordable and you throw your phone. So it's very critical that you reduce the amount of generated power at the receiver, so that you can still carry it and talk, and you don't feel any extra heat generations in your receiver. Perform digital combining for all the highly quantized received signal. We call the signals coming out of ADC highly quantized because it's 1-bit, using 1-bit, either 0 or 1. 0 is down, 1 is up. Promising high signal to noise ratio capacity results at high signal to... Many open topics related to this transceiver structure. So including channel estimation, how to estimate the channel, equalization, constellation, optimization, and many others as well. So we need to be very careful with this design, although it reduces the power consumption, the complexity, but also it kind of reducing the resolution here, which is not very desirable. So we have some applications for MIMO systems, and one of these applications is what's called line of sight MIMO. Line of sight MIMO, which is very suitable for massive millimeter wave line of sight MIMO systems. So before that, let's emphasize the fact that MIMO systems can work well when you have a rich scattering channel. Again, repeat this one more time. MIMO system, especially spatial multiplexing MIMO system, creating multiple beams, multiple streams for different users, can work well when you have a rich scattering channel. Why? Because the rich scattering channel will create some basis function that are orthogonal to each other, that are independent of each other, and based on these independencies between the vectors, you will be able to make use of the channel to be able to differentiate these streams from each other. So basically fading, which is a phenomena a phenomenon we don't like in most wireless communication system. In MIMO, we like it too much. Why? Because it helps us detect and distinguish our streams from each other and separate them and get our data back. However, if you have line of sight MIMO, where you don't have rich scattering channel, you don't have multipath fading, you don't have these reflections, MIMO will not be able to function well in a normal practical implementation case, where you have the transmitter, a base station, and the receiver is mobile phone, and you have a distance of 1 kilometer, for example, in a realistic environment in cities or urban rural areas. So what's the point then? MIMO cannot work in line of sight. It doesn't work in line of sight. To make it work in line of sight, you need to have some, you need to satisfy some conditions. And one of these conditions is the distance between the antennas, the transmitter, should be comparable to the distance between the transmitter and receiver. Can you imagine this scenario with me? Again, one more time. Can you imagine this scenario with me? The distance between the antennas at the transmitter and the receiver should be comparable, means very close to the distance between the transmitter and receiver. This is really insane. Can you give me an application where you have this case? You have an access point, and I tell you, both the antennas at the access points away from each other in such a way, the distance between them is the same as the distance between the access point and the receiver. Can you find a practical single application for this? Line of sight MIMO requires these conditions to make it work. And this is not feasible, not practical, not desirable. However, recently they found certain applications that might need this. Where do you have these applications? In data centers and chip-to-chip communication. In data centers, and when you have servers storing the data, and these servers are in continuous, like if the server gets full, needs to communicate with the server and transfer the data to it. So they are very close to each other, and you have hundreds of cables coming from this server to that server. So instead of using these cables, you can save them. Let's say each cable is $100, and you have 100 cable, you have 100, you have $10,000. You can save these $10,000 by just employing MIMO line of sight connection. And this is amazing, great application for this, but it cannot work line of sight MIMO. It cannot work for practical wireless, which is getting practical cases where you have the distance usually between the transmitter and receiver more than 100 meters, and you cannot place the antennas at the transmitter to be apart from each other by 100 meters. It doesn't make sense. You cannot design it such way. But in data centers, for example, YouTube, Facebook, Google centers, Amazon, Azure, these things, it's kind of a promising application where you can replace the cables and save money. So here, the point here, multiple parallel millimeter wave line of sight MIMO links can be established for this kind of application. System relies on antenna element spacing from diffraction limited optics. Links are robust to deviation in antenna alignment and array positioning. The data rate, the most promising thing, can reach up to 300 gigabit per second. Almost, if you increase the number of antennas enough, you can reach to 1 tera. And the applications is data center and chip-to-chip communication. And as you can see, angular separation at the transmitter here, we are talking about this angle. This angle is basically theta T is that we care about. Theta T in the range of T over R. Link range, antenna spacing. D is the antenna spacing between the antennas, and R is the link range, the distance between the transmitter and receiver. And the angular resolution can be given by this formula. But this is the thing. In normal communication system, theta, this theta, since the receiver is very far from the transmitter, the theta goes usually to 0. Yes? When the receiver is here, yes, this is the receiver, and you're transmitting from here to here, so the distance r is very large, and the spacing between the antenna is very small, so you are dividing something very small over something very large. It becomes almost 0. This theta in microwave, in normal communication cellular systems, it's close to 0. So this fact is really very important, very crucial, very critical to remember all the time, that fading helps us implement MIMO, make use of MIMO. But when we don't have fading and when we have line of sight scenarios, things become difficult and not feasible to implement it. But luckily we found some applications that can be usable. So MIMO with polarization, we said my millimeter wave is very sensitive to polarization, and if you are going to use MIMO with millimeter wave, you need to be very careful with this. Therefore, it's very recommended that you use two polarization at the transmit antenna, one vertical, one horizontal. Why? Because if the vertical, for example, gets reflected off an object, and when it gets reflected, it can change the polarization. So you are assuming the transmitter and receiver have the same polarization, vertical. You transmit it vertical. The vertical hits off an object, gets reflected back. The reflection changes the polarization, and now you have horizontal while the receiver has vertical. You don't get any induction current. You cannot detect or receive your data successfully. To avoid this case, we kind of use two polarization, so that if one of the polarization, let's say vertical, was reflected wrongly, is not aligned with the receiver, the other will compensate for that, and the other will be aligned with the polarization of the electromagnetic field at the receiver. So polarization works at millimeter wave, helps orthogonalized channel. System design needs to deal with challenges, mobile misorientation. If you misorient your phone, you might not be able to get your signal, especially if there is no rich scattering in the environment. Mobile orientation can be estimated without explicit channel knowledge. Diversity and multi-users are issues to look at. So it's current research in academia as well. Now let's, having talked about these issues, the MIMO design for millimeter wave and polarization, and some of the special things that we need to take care of and consider while we are designing the system. Now let's talk about the consumer applications of millimeter wave MIMO currently in the industry and in the market. What consumer applications we have, and what are we having so far? So we have, let's start from 5G. 5G, the second phase, is expected to use millimeter wave, which are the high frequency signals. The new thing here, you know, the 60 gigahertz signal, or even in 5G, there are 3 bands they are saying they will use for 5G, or the improvement of 5G. The first band is something like 26, 27 gigahertz frequency. The third is around 36, and there is one at 60, and there is another one at 76 gigahertz, something like this. Now, if you think of 26 gigahertz, this frequency is basically used for TV communication with the satellite. 26 gigahertz is the frequency used to transmit your TV channel, to receive your TV channel in your satellite dish at your home. Yes? 26 gigahertz. So it's a frequency we use for satellite communication and for TV purposes. So it's kind of backhaul. A human being can never usually come on top of the dish and put his hand or something like this or block it. And usually when you install the dish, you bring a technician to install it for you, and the technician, when he installs it, you see how much careful he is while he's aligning the antennas. And the antenna is basically, let's say this is the dish. The antenna, since you are using for TV 26 gigahertz, the antenna is basically this tiny thing here, because it's 26 gigahertz, very high frequency, means very low lambda. Lambda is very short, and you have this tiny antenna here, and this is just to reflect and concentrate and gather energy and concentrate it to the antenna, so that the antenna can have enough energy to decode the signal, to increase the signal to noise ratio. So think with me, we have satellite communication using this signal long time ago. Now we are bringing this signal, this frequency, and want to use it for internet, not for satellite communication, and for radio access, which means base station and mobile handset. So this is kind of, since that you are always there, in most of the cases there will be some blockage, some uncertainty going on between the transmitter and receiver, so you won't be sure that whether you will receive the link correctly or not. You don't know. So what are we so as you can see, this 26 gigahertz is around for long, it has been around for a long period of time, but we are using it now, instead of using it for backhauling or TV satellite communication or other application, we are now using it for radio access internet. So we have 5G, we have a product in the market called Silicon Image Ultra for HD, Ultra HD. We have Ultra HD, and we have LAN, local area network built with WiGig, and we have personal area network, wireless HD. And one of the first companies that were able to design a chip that works at 60 gigahertz is called Wislab chip. And this company was bought by Qualcomm, and right now is part of Qualcomm. So we have the wireless HD. All these, imagine these products around 2014, 2013, 2000, even 2008. We have technologies running at 60 gigahertz here around this. WiGig 2010. There are access points in the market. I don't know whether you have used them before, but they are available in the market. So what else we have? Major interest in wireless application, yet radar far. Even I told you the gigahertz bands 26 and 30, they are used for TV communication and this, but also there is range of frequencies that has been used for radar communication, for car communication. There are some advanced cars where they have radars in front of them to detect and help driving the car safely, and these radars are basically using 30, 40, 60 gigahertz communication. For example, this is a car concept of automated radar. So there is a radar in front, radar in the back. It can help the car to stop, go, parking aid, for lane change support, blind spot detection, pre-crash from both sides, long-range radar, and this is really already implemented and used in the industry. Long-range radar operates in this range of frequencies. These are the frequencies used, 76, 77. There are cars that are using these radars. Of course, why they use high frequencies? Now, one of you might ask, why do they use high frequencies? Because when you go to higher frequencies, the bandwidth is larger there. When the bandwidth is larger, the symbol duration is shorter, which means you can get more resolution of the things. It becomes not radar, becomes like imaging. You are taking image or photos of the scene just by signals. Also, in hospital, in medical hospitals, also they use some of these frequencies for screening the brain, screening the chest, seeing the images inside your body. With these frequencies, they use them for imaging, magnetic resonance, MRI. I don't know the exact name of that picture that they take it in hospitals sometimes for the patients. So they use it for imaging as well. We have the short range radar operating at 24 gigahertz, and we have the medium range radar operating at 7781 gigahertz with a bandwidth of 600. So these are different types of radars that are using these bands, and most of these are used with cars. What are the main research issues in automotive radar? In automotive radar, the main research issues are as follows. You want to reduce the cost, the weight and size. You want autonomous driving. You want basically surround field overview, improvement in 4D resolution, fusion, joint vehicle, higher frequency electronics and interference, clutter. All these research are related to automation going on, and many research groups are working on. 1180, this figure shows you the development phase of WiGig. It started in 2008 and they manufactured it around 2011. It was ready almost, and the company that produced the chip and installed, and they are working on it. So companies are pushing and many alliances. The key motivation for these technologies is basically data-hungry apps, HD TV streaming, rapid synchronization, real-time gaming and streaming, and many others. 60 small form factor. So, and most of these products are already in the market, and in IEEE 802.11ad, which is WiGig technology, we have the physical channel, single carrier physical channel, OFDM physical, low power single carrier physical, and so on and so forth. So you have also multiple antennas for transmitter and receiver, support only single stream phase shifter in WiGig, analog beamforming we are using, and 60 and 32 antennas are common. These are the ones that have been used so far. So training to implement single stream MIMO, one of the key challenges to millimeter wave as well, beam training. And beam training is basically you try to find the best beams at the transmitter and receiver that should be allowed you connect and communicate successfully and convey your data without any problems. So you have the sectors, the beam patterns, and there is kind of feedback between them until they find the beams. The transmitter sweep the beams, the receiver does the same, and then they exchange some feedback until they agree on the beam that they want to communicate over it. It transmit, sweep, trains a combination of sector. Think of it like this channel estimation, trying to estimate a channel before you communicate. And after that you do beam transmit or receive antenna configuration. And you need also some kind of tracking, which is periodic refinement over a small number of antenna. Research challenges in millimeter wave can be classified under the following umbrellas. There is a direction focused on trying to come up with techniques that can bring better beam alignment and tracking. Another direction focused on multi-stream MIMO. Another direction going towards even higher frequencies, terahertz even, terahertz, that's coming after millimeter wave, and signal processing algorithm, backing and antenna domains. If you are good in antenna design, if you are good in signal processing, if you are good in algorithm, if you are good in circuit design, if you are good in MIMO, if you are good in higher frequency analysis, if you are good in alignment, you can have some contributions in this domain. So it's very big, very massive, have many directions, and people are working